let's get into the gas laws, my friends, and I'm going to twist this a little bit. Normally we do all these what are called the simple gas laws, and we build them up into like the ultimate gas law, the ideal gas equation, which is not quite the ultimate one. You'll find out. I like to start with the big one and then break it up and see how we can derive all of the other gas laws from it. So we're gonna do a lot of derivation here. All right. So we already looked at the different parameters of a gas that define the gas's behavior: pressure, volume, particles of gas in terms of moles, and temperature, right? Well, if you put them all together, we will find that assuming, remember kinetic molecular theory, assuming that the gas particle volume is so small it's effectively zero compared to the volume of the container, and there's no interactive, attractive, or repulsive forces. Only if they directly collide will we take into account any kind of interaction. But if they have a nearby, like an asteroid just missing, we're just going to assume they don't even notice each other. Assuming those, we get what's called an ideal gas. So that's where the ideal gas equation comes from. And we'll find that the pressure times the volume is equal to the moles of the gas times a constant, right? Because normally without the constant, this would be a proportionality. Pressure times volume is proportional to the moles times the temperature. To make it an equality, we need a constant, and that is R, the universal gas constant. I'm not going to derive that for you. Together, you get PV. I see people call it PVNERD. I call it the pervert equation. Hey, whatever works for you, all right? Personally, I'll give that to you on exams, but you'll have it memorized in no time. But all the other ones, I want you to be able to derive from it. I love deriving equations. All right, what do all these mean? We'll take a look at what this is in a little bit. R is called the gas constant or universal gas constant. Depending on the units of pressure, you're going to get different numbers, right? We got bars and pascals and atmospheres and torr and oh my God, pounds per square inch. So many pressure units. If we use atmospheres, right? So our volume is in liters and our pressure is in atmospheres. Obviously, moles will be in moles. Temperature needs to be in Kelvin. Otherwise, you can get like negative pressures and stuff. So you can't use degrees Celsius or degrees Fahrenheit. It's got to be in Kelvin. Must be. Temperature in Kelvin. Remember that. Wouldn't make sense otherwise. So if we plug in those units, you'll get 0.082057 liters atmospheres per mole Kelvin. I've used 0.082058 in the past before, so not going to be a big deal out to that many decimal places. So 0.082057 technically. Now, if we use the SI units of pascals and use the volume in meters cubed, you'll get a value of 8.3145 pascals times meters cubed per mole Kelvin. Well, isn't it nice? A pascal times a meter cubed is a joule, unit of energy. We introduced this in the last postulate for the kinetic molecular theory when we related the Kelvin temperature to the average kinetic energy of the gas sample. That R came into play. So we're going to be using energy units for that. So whichever one you use, we'll never use the pascal times meter cubed, blah. But that is effectively a joule. So if we wanted, we could get a conversion factor between liters, atmospheres, and joules. 101, I forget. I don't want to calculate it right now, but we could. This will be by far the most common one we use. Anytime we use energy, we need an energy unit. We're going to use 8.3145 joules per mole Kelvin. I'll give you both of these on exams. We're good? So we're going to focus on this one right now because we're not going to deal with energy stuff until a little bit later. So what we're going to do is I'm going to look at this for static conditions and non-static or changing conditions and show you how this changes a little bit. Then we'll derive all the other gas laws from it. This will be a nerdy, fun little trip. All right, just rewriting what we had on the other board. PV equals nRT. That's the ideal gas equation for static or non-changing conditions, right? We're not altering anything. It's just 5 parameters. One's a constant, so there's only 4 variables. As long as I give you 3 of the 4, you can calculate the other one. The math in gas law calculations is easy. If I give you pressure, volume, and moles of gas, you can solve for temperature. If I give you temperature, moles of gas, and pressure, you can solve for volume. Pretty straightforward to do. I'm going to do all the gas laws first, and then we'll do calculations probably in another video. I want to show you all the different variations of this. We're going to end up deriving like 8 or 9 different equations from this one. Let's derive the first one. What if we alter something? What if we have a gas sample and we change the pressure, change the temperature, and it's like, oh, what's going on here? Well, let's move all the variables to the left and have the constant to the right. So would you agree that pressure times volume divided by moles times temperature equals the constant? That's a constant, right? So this would be true initially and true after we make any changes. So this is before changes. Let's call that state 1. And then let's alter the parameters, and this would also be true after. Let's call this state 2. This is after the changes. Oops, if I could spell. All right, we good? But regardless, they must equal R. So if the state 1, PV over NT equals a constant, and PV over NT at state 2 equals a constant, they both equal the constant, they must equal each other mathematically. Right? Hey, well, that's a good thing for us. Therefore, let's call this state 1. So let's say P1V1 over N1T1. All state 1s, or you could do initial if you wanted. You could do sub I. Since that equals R, that must equal that. So let's call this state 2, P2V2 over N2T2. Or you could say initial final. Up to you. It doesn't matter. So this gives us the ideal gas equation for changing conditions. Ho, 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 changing conditions. So that is given the name the general gas equation. So let's write that down. So that's the general gas equation. That I would expect you to be able to derive from this, right? Do it just like that. So I'm not going to give this personally on an exam. I think you could derive it. That's an 8-variable equation, but it doesn't have R in it at least. As long as I give you 7 of the 8, you can calculate the 8th. Nice, huh? So this is for changing conditions. For changing or non-static conditions. Or another way to say it, it's the ideal gas law for changing conditions. This is the ideal gas law for non-changing conditions. Yay! So what we're going to do, so I would take an entire piece of paper and I'm going to set up empty circles for all the different gas laws we're going to derive from these. It's going to take this whole video and then we'll do some calculations on the next one. So get that whole piece of paper, boom, and we're going to fill in some bubbles. Here's what I want you to draw on your big piece of paper. It's going to be tough on my little tiny board here, so I might need to break it up into smaller bits. But we've got the ideal gas equation. That'll be the main one, number 1. That's the only one I'm going to give you. You need to derive a total, there'll be a total of 9 gas law equations. I will give you the first one. You've got to be able to derive the other 8. So we already know how to derive the second one, right? From the ideal gas equation for static conditions. Go to non-static conditions by equating them to the constant R, and you get the general gas equation. So let's do the general gas equation, and let's think about how we can get what are called the simple gas. These are all going to be what are called simple gas laws. They're derivatives or simplifications of the general gas equation. So I'm going to come at you probably from a different way that you've seen in introductory chemistry or high school chemistry or something. So what we're going to do, we got 4 parameters, right? Pressure, volume, moles of gas or number of particles, and temperature. In the laboratory, if you want to understand how one variable is mathematically dependent on the other, like pressure and temperature or volume and moles of gas or something, you got to keep the other ones constant. Otherwise, it's too difficult to tell, right? If I double the pressure, what happens to the volume? Well, I got to keep the temperature and the number of particles constant so I can understand that mathematical relationship. Otherwise, you got too many things changing, right? So what we're going to do is we're going to take 2 of the 4, hold them constant, and if they're constant, so for example, let's say the moles of gas are constant, right? That's a pretty easy thing. Don't change the number. Make sure it doesn't decompose or something. Don't add any more in. So experimentally, that's pretty easy to do, is hold the moles constant. So if N1 equals N2, you're left with P1V1 over T1 equals P2T2. I got too many temperatures there, don't I? you guys should tell me that. I'm like, wait a minute, those would have canceled out. That would have been weird. So if n's constant, then what's left is a simplified version of that. So let's do that. So let's say here, let's hold n constant, going from here to here. So n is constant. Therefore, n1 equals n2. Everybody agree? If n's constant, n doesn't change. So take n out of the equation, and we'll get P1V1 over T1. Take the n2 out, P2V2 over T2. P2V2 over T2. Hey, that's called the combined gas law. Very commonly used in lab. That is the combined gas law. Let's do that in purple here. So that's the combined gas law. That's just the name for it, right? Pretty simple to use. So when you're doing problems with gas laws, you've got this. You can pretty much, if there's something changing, you think about that and go, well, what didn't change? What's constant? Drop them out, bloop, you've got the equation you need. You don't have to memorize them all, right? Some of you prefer to memorize them all. That's okay, but let's just take a look at each one. All right, so that's holding moles constant, by far the most common one we do in lab. Well, let's do the next one. Let's hold temperature constant's pretty easy. Particles is easiest to hold constant, and then probably the temperature. So if we hold the moles and the temperature constant, so let's do that. Let's get this in blue. Let's do N and T constant. So if N and T are constant, you lose both of those, and what are you left with? P1V1 equals P2V2. Ooh, right? So that would leave you with P1V1 is P2V2. So that was studied by, it's called Boyle's law. So Robert Boyle, way back in the 1600s. So let's call that Boyle's law. Way back in 1662. That was kind of the first gas law really studied, because it's probably the easiest one to do. Hold number of particles of gas, temperature constant, look at how the pressure and the volume relate. So what happens if, let's say we double the pressure, right? Well, the volume, in order to keep this equality, the volume would have to change to keep that equality constant. So the pressure and volume are what are called inversely proportional. If I double the pressure, the volume has to drop in half in order to keep this equality constant, right? So they are inversely proportional. If you've seen that term before, what color can I use here? Let's do black. They are inversely proportional. So P and V are inversely proportional. Inversely proportional. Pretty tough to squish this all on one board. I can probably get the simple gas laws in. We'll probably have to do these two on a separate board. So we'll come back to this and fill it in. All right, so combined gas law, pretty simple. You could probably fill it. If you're really feeling adventurous, pause the video and get these other three simple gas laws based on holding any two of these parameters constant. Oh, let's see what you get. So this is by far the most common one, right? Pressure and volume are inversely proportional. A lot of ramifications of that. So thank you, Boyle's law. One of my favorite, next one, is by Jacques Charles back in the 1700s. That's kind of when hot air balloons were getting real popular, right after the American Revolutionary War, getting into all the nasty stuff that was happening in France, with all the guillotining and all that fun stuff. So let's do this. Let's take this, and instead of holding N and T constant, what Jacques Charles was looking at is how the volume and the temperature related. So he held the pressure and the moles constant. So let's go P and T constant. I mean, not P and T. P and N. I'm looking at N and I wrote T. So if we hold the pressure and the moles constant, we're left with the volume and the temperature, which are the two properties that he was looking at. And so they would drop out. So P1 would equal P2, N1 would equal T2. They drop out. You're left with V1 over T1 equals V2 over T2. That is called Charles' law. So that is Charles' law. Let's put that, where are we going to do it? Let's go Charles' law. All right, so we got Charles' law, and that was back in 1787. I will never ask you for dates on my tests, all right? It's hard enough to figure out who it was. But I do want you to know who was what. What is Charles' law? What is Boyle's law? So Charles' law was kind of fun. That was with hot air ballooning. He was one of the first ones to really start putting baskets and valves and things like that on hot air balloons. And we're to have the humans fly. Whoa, that's crazy stuff, man. But does it make sense? We've learned before that if you heat something up, you increase its thermal expansion, the volume goes up and the density goes down. So if you got a balloon and you heat the air up inside the balloon, it thermally expands, which means volume and temperature are proportional. These are proportional. So as the temperature goes up, the volume goes up. You double the temperature, you double the volume. All right? If this goes up, that must go up to keep them equal to each other. Makes simple sense. So if you heat up the air inside a hot air balloon, it thermally expands, its density drops, which means the density of the air inside the balloon is less than the density outside the balloon, and so the hot air balloon rises and then floats around. What a crazy thing back in the late 1700s. Can you imagine being the first one to let's get inside this basket tied to a balloon, heat it up, and float away? You're crazy, or evil, kill him. Imagine landing in, some kind of remote village, and they think you're the devil or something. Stab them. It'd be pretty crazy back then. People thought differently back then than we do now. Things that are obvious to us were not necessarily back then. Right? So imagine 300 years from now, looking back at our time, they're going to be like, man, there's so much you guys didn't know. How are we supposed to know? We're stuck in this time period. Time travel would be so cool. Be able to go in the future and the past and see how people thought differently. All right. So volume and temperature are proportional. As one goes up, the other goes up. Hopefully that makes sense. Now, let's think about it from a kinetic molecular theory point of view. All right. If you increase the temperature, are the particles getting more energy or less? From KMT, remember the fifth postulate, as the Kelvin temperature goes up, the particle kinetic energy goes up on average, which means they're moving faster and hit harder. So the impulse is greater. Remember, pressure, if we're holding pressure constant in this case. So if you're holding the pressure, say it's a balloon, but we're keeping the pressure constant, we have to allow the volume to adjust. So if particles are hitting more often, the collision frequency is higher, and they're hitting with more impulse, that innately wants to increase the pressure. But if we're holding the pressure constant, the balloon must expand, so the collisions are less. It'd be a bigger volume, there's fewer collisions. See what I'm saying? So as you increase the temperature, the volume must expand to keep the pressure constant. Because if you don't, if you keep the volume constant, the pressure goes up. Oh, see that? You can explain all these gas laws macroscopically in lab, and you can do it qualitatively using kinetic molecular theory. That's why I started with that. Let's look at Boyle's law. Holding the number of particles and the temperature constant, so they're all moving the same speed, same energy. The number of particles haven't changed. Say it's just a bunch of people, a bunch of zombies walking in a room, all right? But that room has walls that can move, all right? But we don't change the number of zombies, and they're all just walking at a certain speed. They can't speed up. And every time they bonk into a wall, that creates pressure, right? Well, if I take the room and decrease it in size, those zombies are going to hit the walls more often. See what I'm saying? Even if they're just still walking. So you get more collisions. So with a decreased volume, the collision frequency goes up and the pressure goes up. So you see, decreased volume, more collisions, higher pressure. They're opposites, right? That's why they're inversely proportional. So, and did a different scenario. Here we're changing the temperature, so those zombies are now running instead of walking, which means they're hitting the walls harder and with more force, right? So to keep that pressure constant, the walls have to expand. Right? Just one way to think about it. All right, let's go to the next one here. Let me get my blue color. Let's look at how the volume and the mole number of particles change. So let's hold pressure and temperature constant. So P and T constant. So pressure and temperature constant over here. Let me circle these. So that's the general gas equation, ideal gas equation, Boyle's law, Charles' law. Sure, you've heard of all of these already. So if we hold the pressure and the temperature constant, we're left with the volume and the number of particles of gas. So V1 over N1 equals V2 over N2. So V1, let me get the right color here. Right? Take out pressure, take out temperature because they're equal if they're constant. See, we're holding two constant. And so this is Avogadro's law, looked at by Amadeo Avogadro. So let's write that in. Avogadro's law. Avogadro's law. So that was back in 1811. And again, the date's not critical for my class. Let's think about Avogadro's law, right? Let's look at the proportionality of these. Let's hold the temperature constant, so the particles can't move faster, the zombies can't start running. Let's hold the pressure constant, all right? So the volume is allowed to adjust to hold the pressure constant. So if I have say a balloon, and I blow more particles into it, see what I'm saying? But I can't let the pressure, so if I blow more particles in, now I have more collisions. The collision frequency goes up, which means the pressure wants to increase, right? Because pressure is impulse times collision frequency from kinetic molecular theory. But if I need the pressure to stay constant, the balloon must expand, because when you expand the balloon, the pressure drops. Okay, so as the pressure is trying to increase, the volume is increasing to counteract that pressure to hold it constant. So as number of particles goes up, the volume must go up proportionally to keep this in equality. Does that make sense? More particles, more collisions. To hold the pressure constant, the container must expand in the process. I think Boyle's law is a little easier. Actually, Charles' law is probably the simplest one to explain. Holding pressure constant is kind of weird. So Avogadro's law, Charles' law, Boyle's law. One more that's not counted as often, but let's look up in here. Let's look at how all of these relate to volume. So pressure volume, temperature volume, moles volume. We good? So now let's hold volume constant in this one. Let's take volume and moles of gas constant. Okay, so let's go V and N constant. So we're holding the volume and the moles of gas constant in this case. That means the pressure and the temperature are allowed to vary. So P1 over T1 equals P2 over T2. That's the last of the simple gas laws where we hold two parameters constant. A lot of people call this Gay-Lussac's law. It's really Amundsen's law. But I hear most people call it Gay-Lussac's law. So I'm going to erase this right here. We're going to get to those two on the other board. This is getting squishy, isn't it? So this is Amundsen's law. Or some people call it Gay-Lussac's law. Right? I think officially it's Amundsen's law. So if we look at that, let's think about that from a kinetic molecular theory point of view. The number of particles stays the same. The temperature is changing, but now we're holding the volume. So the container can't change, right? The container volume cannot change. So if I increase the temperature, the particles start moving with more kinetic energy. They move faster. They collide with the wall, the inside surface more often, and with more force. There's more impulse. So as the temperature goes up, would you agree? More collisions, more impulse, more pressure. So as temperature goes up, pressure goes up. So these are proportional, right? Just like volume and moles are proportional. Hopefully that makes sense to you. So these are proportional. As well as Avogadro's number. This is also proportional as well, if you want to write that in there. So the only one that's inversely proportional is Boyle's law. But I would expect you to be able to do calculations with these. Pretty simple as long as I give you 3 of the 4. Very easy to do. We'll do that on the next video. And I would expect you to be able to explain Boyle's law, Charles' law, Avogadro's law, and Amundsen or Gay-Lussac's law in terms of it, like a short answer essay question as far as kinetic molecular theory goes. So let's derive numbers 8 and 9, and we'll be done with this one. We'll do some calculations on the next one. All right, let's see if we can derive this one. Brings in a new parameter, actually. So what I'm going to do, we can take the P equals nRT, and this is going to be the top half of our chart on your piece of paper here. Moles, we can do an algebraic substitution. Moles is just mass divided by molar mass. Grams divided by grams per mole gives you moles, right? So if we take the mass over the molar mass, let's use little m for mass and a big capitalized cursive M for molar mass. Sometimes you'll see a double capital M. Doesn't matter. Let's insert that in. So what will happen, we'll get PV equals mass over molar mass times RT. So what I did is I substituted that in for M. Okay, well, yeah, well, you don't have a choice, right? But now moles is gone and we've got mass over molar mass. What we can do now is let's isolate for the molar mass. So molar mass, let's move that over to this side, will be the mass times R times T divided by PV. So if we take the mass times the gas constant times the temperature divided by the pressure volume, we get the molar mass. That's a great way to figure out an unknown gas. Measure all that in lab. Mass can be difficult for a gas, though. Or if we know the identity of the gas, molar mass, pressure, volume, temperature, we can calculate the mass of a gas just by measuring the pressure, temperature, and volume and knowing its molar mass from its identity. This is a cooler one. I don't know what this doesn't have a name that I know of. Let's call it the molar mass equation. I'm not aware of it having a specific name to it. Is that Dumas? Not sure. That might. I have to look into that one. But anyway, molar, I'll just call it, hey, if we're dealing with an equation where we want to figure out the identity of an unknown gas, solve for the molar mass. Or if you know the identity, we can solve for the mass, right? So it introduces those 2 new terms into it, mass and molar mass. Now let's play with this one a little bit. I don't know if you can see it. Let's use this. Let's get over to number 9 here. See if you can derive this one on your own. We're just playing with algebraic substitutions. Gives you a lot of interesting things. So let's take a look at this. Do you see anything on this side that equates to a parameter you've looked at before? One of the earlier videos. Density. What's density? Mass divided by volume. Isn't that right? So density is mass over volume. Do you see the mass? Do you see the volume? Oh, we can insert density into there. So if we look at this, so this would mean molar mass. Let's do this down here. Molar mass would be M over V RT over P. So I'm just rewriting this over here. We good? So that would mean molar mass is the density times RT over P. All right? Can we isolate this for density? So let's bring that up. So density, you out of my density. Let's see, let's bring the pressure up. So we'll take the pressure times the molar mass divided by RT. So we're isolating density, so bring the pressure up and R and T down. So now we get our density equation. And we'll do an example of that on the next video. Probably one of each of those. So all we're doing is these little algebraic substitutions, and now we can get the molar mass in terms of the density of a gas. So can you see how the density depends on temperature? As temperature goes up, density goes down. We looked at that a totally different way in terms of thermal expansion, right? And density is the molar mass. As the particles get larger, bigger molar mass, the density goes up. Hey, we're going to do lots of calculations on the next video.